Okay, so this is the second Walking Talking Mock video for paper 2 of 2018 for the higher tier. There are 7 questions, so use the markers on the video to skip forward if you have got full marks on a question and you would like to move on to the next one. Otherwise, let's get started. So for question 1, we're looking at a card and glider on an air track. Now an air track is we've actually got this piece of equipment at school, although many of you may have seen use the Newton's trolleys in class, because we've only got one of these. Works very similar to an air hockey table. So there is a pipe with these tiny little holes in, and this blower here will send air up a pipe. Okay, and so the air will go into the track, come out of these tiny little air holes, and it will make this glider float on a pocket of air, so it is frictionless. Okay, so this will be important for later on in the question. So the fact that the air track reduces the friction to basically 0. Okay, so it says that the glider is released from rest and moves along the track. So if you have a look at the setup, you've got a mass here. That mass has got a weight that acts downwards. And because the string is over a pulley, there will be a tension in that spring, providing a force to the right that pulls this glider to the right. And because you know that force is equal to mass times acceleration, okay, because there is a force being applied to the glider, there will be an acceleration. So it will, when you release it, so if you've got it stopped at this position, as soon as you let go, it is going to accelerate towards the right. And we use a double arrow like that to show that it is accelerating towards the right. Okay, and then you've got these 2 light gates. You've got one light gate at this position and another light gate in the second position. And what that's doing is this piece of card is on top of the glider is going to cut the light beam in the first position and then the second position, and it will measure its initial velocity here, and it will measure its final velocity v here, and from that it can work out its acceleration. Okay, these might help you understand that. Just understanding this diagram is going to help you understand the rest of the question a little bit better. Okay, carrying on reading the question then. This is the line that if you miss it, you will completely misinterpret the question. So it's really important to read the whole question. It says that the mass holder hits the ground before the card passes through the second light gate. Okay, so we have a situation where there's the ground. This mass holder is going to hit the ground and land on the ground, okay, before the card has passed through this second light gate. What that means is, if I draw a force diagram of what's going on, before the weight hits the ground, there is a string providing a force that is equivalent to the weight, pulling it to the right. Okay, so that would be the force in the equation that's showing us that it will accelerate. There is a force, there is an acceleration. However, as soon as that weight has hit the ground, then there is no force. Okay, so if I was to draw a force diagram of that, it would just look like that. Okay, the block is being pushed up by its pocket of air, but there is no force acting to the right now. Okay, so we could say that the resultant force is 0. Okay, and if there is 0 force acting on an object, there will be 0 acceleration. So which 2 statements describe the effect that this would have on the glider? That's what effect does the fact that the mass has hit the ground have on the glider? First of all, we can say that the acceleration would decrease to 0. So because there is no force, there is no acceleration. And the second one, the resultant force would decrease to 0. Well, we've just explained that. Okay, so because there is no resultant force, there is no acceleration. If you had not read that second line in the question, you would have potentially thought that we were in this situation where there was a resultant force and it would speed up, and so you may have selected any one of the other or any 2 of the other 3 thinking you were right. So it's really important to read the question. Okay, so moving on to the next question. This is one of those questions where it is actually more about the common sense than anything else. Okay, so the mass the mass should not hit the ground before it passes through the second light gate. Suggest one way, okay, one way that the student could stop this happening. There are two, and either of them would get you 1 mark. But you, if you were to get one of them wrong or phrase one incorrectly, you may talk yourself out of a mark. So try not to suggest 2 and hedge your bets in a question like this. Pick the one that seems most logical and go with that. And so in this case, the 2 answers: shorten the string or move the light gate closer, the second light gate closer to the first. So if you go back to the diagram, it's fairly obvious that if the string was shorter, so if the mass was higher up and the string here was shorter, then by the time the said glider has passed through the second one, it wouldn't have hit the ground. Or the other option is to move this entire second light gate. If you were to move it closer to the first one and move it to the left, then obviously again we've got a situation where the card has passed through the second light gate before the mass has hit the ground. Okay, so you don't need to write both of those. Either one of those answers would get you the mark. So moving on to question 1.3. This was covered. We did this when we did the unit on graph skills and table skills. So we're spotting mistakes in the table of data. So she did the experiment she increased the resultant force, recorded the acceleration, she calculated the acceleration. Each test was done 3 times. Table 1 shows the results. The student made 2 mistakes in the mean acceleration column. So if you read the full question, it even tells you that the mistakes are in this column. That doesn't mean that she didn't use this data in the table to make the mistake, but the mistake that she's written down is actually in one of these 2 of these results. You have to identify the mistakes and suggest how to correct them. So the first mistake is for the 0.2 Newton force reading, mean acceleration calculation, and here the mistake she has made is that she has written the answer to too many significant figures. So all of these numbers are to 2 significant figures. This should be written to 2 significant figures as well. It should be 1.3. And the second mistake is in this row here for the 0.98 force value for the mean. And here you can clearly see with all of the others, 2.6, 2.5, 2.6, they're all about the same. 3.8, 3.8, 3.9, same. In this one they are even exactly the same, 5.1. With this one, 6.4 and 6.4 and 7.2. 7.2 clearly doesn't fit the pattern, so she should have ignored 7.2 when she worked out the average. So the average of 6.4 and 6.4 by itself is obviously just 6.4, so that's what she shouldn't have written. So to answer these questions, that's what you need to do. You need to write down what the mistake was that they made. In the first case, 1.26667, and you can either write down the mistake they actually made or write down where they wrote it wrong. So in this case, the mean value for the 0.02 Newton result, and then you need to write down how what they should have written or what they should have done differently. So in this case, they should have written 1.3, or you should have written just write the value to 2 significant figures, and 2SF is fine. Okay, so because obviously the 6 is here, round up to make that 1.3 to match the significant figures of the other results. And in the for the second mistake, the mistake was writing 6.7, or the mean value for the 0.98 Newton result, and what they should have written is 6.4, or what they should have done is ignore the 7.2 anomaly when the mean is actually calculated. Okay, so there's your 4 marks for that one. And finally, write a conclusion for this investigation. So if you look back at table 1, you should be able to spot, if I do it in a different colour, you should be able to spot that this roughly goes up in 1.3 every time. So 1.3, 2.4, roughly 3.9, roughly 5.2, roughly 6.4. Okay, and this one goes up, the force goes up in about 0.2 every time. That's roughly 0.2, roughly 0.4, roughly 0.6, roughly 0.8, roughly 1. Okay, so as the force increases, the acceleration is increasing by roughly the same rate every time. Okay, going up in about 1.3. Now you don't have to write the values for that, but you are expected to be able to spot that there is a roughly directly proportional relationship there. So there are actually just writing as force increases, acceleration increases would get you the mark in this case, but the better answer is to write that force is directly proportional to acceleration for 1 mark. So moving on, 1.5. The student used a constant resultant force to accelerate the glider. The student changed the mass of the glider and calculated the new acceleration. So this time, before, she was keeping the mass constant, she was changing the force, and she was measuring the acceleration. Now she is going to keep the force constant, and she is going to change the mass and record the acceleration. So we would expect a situation here where these two things, the mass and the acceleration, are inversely proportional, because for this number, for the force to remain constant, if the mass is increased, we would expect the acceleration to decrease. So we're expecting these things to be inversely proportional. Okay, so let's have a look, because the question asks you to do two things. It asks you not only to plot the results, but it also asks you to draw a line of best fit. So let's have a look, and we'll plot these points. So 0.06 and 3.5 is up here. 0.08 is 2.6, which is about there, and we'll do the rest. Okay, so that's the points plotted. Now, as for the line of best fit, well, if you take a ruler here, you can quite clearly see that if you bring it up to the point, that is not a straight line, because even from there, you can see when you put it in the middle, it's moving away from the line on both sides. There is definitely a curve there. So I'm not going to use a ruler. Instead, I'm going to, if I turn the page upside down and use the backhand of my, to draw a smooth curve, you can just draw a smooth curve as close to as many of the points as possible, and that would give you a curve of best fit. So don't always assume that it's going to be a straight line. Okay, so that's 1.5 done, and 1.6, the relationship between mass and acceleration. The answer they're looking for is that mass is inversely proportional to acceleration. Again, you could have written that as mass increases, acceleration decreases, but when you see a curve like that, where as mass increases, acceleration decreases on a curve, chances are it is an inversely proportional relationship, and that's the one that is on the mark scheme for 1 mark. But like I say, it does allow you to write as mass increases, acceleration decreases. So if you're not sure, write that as a backup, but try and get practice at spotting inversely proportional relationships. So that is question 1. Moving on to question number 2, we're going to look at magnets. So with this question, the first one, a magnet produces a magnetic field. The diagram shows which diagram shows a magnetic field around a bar magnet. It's clearly not that one and not that one, but the other two, the lines look the same, but the clue is in the direction of the arrows. In these ones, the arrows go from south to north. Okay, so the arrows are going in to the north end, whereas in this one, the field lines are always going from north to south. Okay, so they're always going from north to south, and their arrows are coming out of the north end and into the south end, and that is the one you're looking for. Okay. Figure 3 shows 3 metal blocks. The blocks are not labelled. One block is permanent magnet, one is iron, one is aluminium. Describe how another permanent magnet could be used to identify the blocks. Okay, so you need to identify all 3 blocks for 3 marks here. So what you want to do is write and answer the 3 parts to this question. So if you say what effect a magnet would have on each of these 3 blocks, if it was aluminium, it would have no effect on it whatsoever, no effect. If it was an iron, iron is a magnetic material, so a magnet could only attract another magnetic material. Okay, just like your fridge magnets will only attract themselves to an iron or steel. Steel contains iron, so it is magnetic. It can only attract itself to a fridge door. However, a magnet is capable of both attracting and, that's the important bit, repelling another magnet. Okay, so if it approached this block and it didn't move at all, then that would be the aluminium one. If it approached this one and at both ends, regardless of which end it was attracted to it, then this would be the iron block. And if this one, the third one, if it put the magnet at either end, and on one of them it was attracted to it, on the other one it was repelled away from it, then that suggests that this one is the magnet. Okay, so make sure for 3 marks that you've written 3 sentences there, all of which help identify the 3 blocks. So figure 2.3, question 2.3. Figure 4 shows a toy crane. The toy crane uses an electromagnet to pick up and move the blocks. Explain how this electromagnet is able to pick up and move the blocks. So, with these long answer questions, it's really important that you lay out your answer using bullet points. You are encouraged to use bullet points, and with these kind of long answer questions, you want to tell a story. Okay, and look for clues in the question. Okay, they have clearly pointed out this switch for a reason. Okay, so what's going to happen is you're going to lower the electromagnet, you're going to turn the switch on, it's going to pick up some of these blocks, you're going to then be able to move them. Okay, it's a toy to play with these blocks, and when you've moved them, you're going to release the switch, open the switch again, and it will turn off and drop the blocks. That's what's going to happen. So tell the story of how that happens. So the first thing to happen is that you close the switch. Okay, so say that. So the switch closes the circuit. When the switch closes, so this allows the current to flow along the coil of the electromagnet. So if you just have a look, they've clearly drawn in enough detail on the electromagnet for you to see that coil. Okay, so they want you to talk about it. This then in turn produces a magnetic field around the coil. Some of you might remember the lesson where you took a coil of wire, okay, and when you run a current through that wire, you get a magnetic field around it that actually looks very similar, identical in fact, to the magnetic field produced by a bar magnet. And when that happens, when a magnetic field is produced around a coil of wire, if you have a magnetic material in the core of that coil, so in the middle of that coil you have an iron bar, and that's what this iron U-shaped bar is there, that core will become magnetized. So that is the next part in the story. Okay, so this magnetizes the iron core of the electromagnet. This then, of course, when you lower the toy down to the blocks will be attracted. So make sure that you're answering the question. So the question says, explain how this electromagnet is able to pick up and move the blocks. So you still need to finish answering the question. So you've explained how the electromagnet has turned on and become an electromagnet. Now you need to explain how it's able to move the blocks. Obviously the blocks need to be attracted to the electromagnet. So when lowered to the blocks are attracted to the electromagnet. And then finally, you might be tempted to then say the whole thing in reverse and talk about what happens when the current stops flowing and the switch is opened. But I feel like for 6 marks, it's only a 6 marks question. By the time you've got to this point, you have fully explained how an electromagnet is set up. I think it's fairly implied that if you undo the switch, then everything is reversed. But you do need to finish off and finally answer the question. So just put that switching off the circuit switches off the electromagnet, which releases the blocks. Okay, so make that last point just to round off the answer, but without waffling too much, and that would be your 6 marks for this question. Okay, moving on to question 3. Question 3 is about an ice skater. They have started you off with a nice simple question. What is the, now with these questions, what is it when you see a write down the equation that links? You've got 3 things here: mass, momentum and velocity. You should be using these 3 things and only these 3 things in your answer. Okay, use the words of the question. So in the equation that you will have learnt from the from your revision sheet, momentum is equal to mass times velocity. Okay, and so for question 3.2, the symbol equation for that one is that momentum is P is equal to mass times velocity. You don't need to put that for the mark, but it will help you with 3.2, because in this one you know the velocity, you know the momentum, and the units are in meters per second and kilogram meters per second, so we don't need to convert the units, but we are expected to calculate the mass of the skater. So if you want the equation triangle for this one, it is that momentum sits on the top, mass and velocity are on the bottom. Okay, so if you cover up mass, what's left is, for the equation, mass is equal to P divided by V. That's what's left over once you cover up the thing that you're trying to make an equation for. Or equally, you could just remember how to rearrange that equation. So mass is equal to momentum divided by velocity. Show you're working out. So it is 200 divided by 3.2, which comes out to be 63 kilograms. Now there are 3 marks for this question. 3 marks for this question. One of them is for rearranging the equation, one of them is for showing you're working, and one of them is for the answer. So you do need to make sure you do all of those things. Okay, don't simply write the answer. If you just write the answer and you get it wrong, you get no marks, but also if you just write the correct answer, they may still expect you to show you're working out. So, moving on. 3.3. Skater A bumps into another skater B. So in this situation, you have got, it tells you that skater B is stationary and skater A collides with him, okay, with a certain velocity, initial velocity of u, and then afterwards, okay, they move off together as one. So A and B move off together with a second velocity. Now, logic would tell you that if this one is stationary, so if B is stationary and has a velocity of 0 meters per second, that if they combine and move off, that V is going to be slower than u. Okay, and the physics will tell you why. Because the momentum, we know that the momentum, the total momentum in this picture before they collide is equal to the total momentum of their combined momentum afterwards. Because momentum is equal to mass times velocity, if their momentum has stayed the same, but then mass is now their combined mass, the mass has increased, that must mean that the velocity has decreased. Okay, so how do we put this into a 3-mark answer? Okay, first of all, you need to state the law of conservation of momentum. That's always the starting point for these questions. Okay, so the total momentum before the collision is equal to the total momentum afterwards. So hence, because the momentum beforehand, the momentum of B is equal to 0 because he has no velocity, and if his momentum is equal to mass times velocity, if his velocity is 0, his total momentum is 0, because anything times 0 is 0. And so this one has a momentum, and whatever his momentum is before he collides with B, that momentum is now going to have to be shared between the two of them. So it's worth stating that. So you can state that the momentum of A is now shared by A and B after the collision. So therefore this must mean that the momentum and velocity of A decreases, but the momentum and velocity of B must increase. Okay, and so I have answered the question, okay, because it asks you to explain what happens to the velocity of each of the skaters using the conservation of momentum. It even tells you to use the conservation of momentum at the end of the question, so make sure you state that at the start of the question. Okay, it's always a good starting point, but make sure you finish off your answer by answering the question, explaining what happens to the velocity. So if the momentum is gone, if the momentum has decreased, the velocity will decrease, and if the momentum has increased of B, then its velocity of B will increase as well. So that's what's happened. A has hit B and slowed down, but obviously B was stationary beforehand, so B will have sped up. Okay. Right, moving on to question number 4. So question 4 is all about springs, so more about forces. Which Newton meter has the spring with the greatest spring constant? So if you look at what the spring constant is, we know that force is equal to spring constant times extension. The spring constant is how stretchy a spring is. Its units are newtons per meter. So that's, if you look at the units, it is how many newtons you need to get a 1 meter stretch in your spring. So, for example, if you have a spring constant of 5 newtons per meter, opposed to a spring that has a spring constant of 10 newtons per meter, this spring here is the stiffest spring. Okay, this one you would describe as stiff because it needs a whole 10 newtons to stretch it 1 meter, whereas this spring you would describe as the more stretchy spring because it only needs 5 newtons to get the same amount of stretch. Okay, and obviously this one has the 10 newtons per meter spring constant, has the greatest spring constant. It's got a larger value than this one over here that's just 5. Okay, so the spring with the largest spring constant is the one that needs the biggest force in order to stretch it by the same amount. So if you have a look at this, which Newton meter has the greatest spring constant, it's going to be the spring that needs the most force to stretch it by the same amount. Well, this spring Newton meter A needs 2.5, B needs 5 newtons, C needs 10 newtons, D needs 20 newtons to stretch it from the start all the way down to the bottom of the Newton meter. So the answer is D, and the reason is that it needs the greatest force to extend the spring by the same amount. So you don't need, if I just put a blue box around that, you don't need to do any of this stuff here. It was just to explain the concept of a spring constant. But notice that I have used the word extend rather than stretch, and I've used the word force. So I'm just making sure I'm using the right keywords in the right places. Okay, move on to question 4.2. So this question is all about errors. So the Newton meter in figure 7 will give you an error when used, and if you notice there's nothing hanging on the Newton meter at the moment, and yet the needle is not pointing to 0. Okay, so we call that type of error, we call it a zero error, or it is sometimes known as a systematic error. Okay, a systematic error. Systematic error being one that is normally where something is wrong with the equipment, and your answer is going to be wrong by the same amount every single time. Okay, so every time you hang something on this, your result will be out by 1 Newton because it didn't start at 0. Okay, so there's 2 easy ways to correct this. You can either adjust the meter back to 0 when it's unloaded, so remove any loading from the hook, and if you can, sometimes these devices have got like a little spring at the top, a little dial, and you can twist that dial and move the needle back up so that it's at 0 when there's no loading on it. Or, and this is important, or you can record the values, then subtract the zero error, in this case 1 Newton, from each of the readings. So every time you add a new weight onto here, just make sure you take off this 1 Newton zero error each time. Now it's important that it's or, because if you were to do both of them, then you would have a systematic error the other way. You go back to 0 and then you'd be one Newton too few each time you took a reading if you then did the second thing as well. It's only 2 marks, so you only need one of these 2 answers. You don't need both, but there are 2 options for you there. Okay. And 4.3, a student hangs the weight onto the Newton meter. The energy now stored in the spring. So I'm already thinking, now that we're talking about energy, I haven't even read the rest of the question yet, and I'm already thinking that I'm going to need to use the equation that E is equal to 1/2 times K times extension squared. Okay, and I believe that equation is on your formula sheet. So the energy now stored in the spring is that 4.5 times 10 to the minus 2 joules. The student then increases the weight by 2 newtons. Okay, so that might be important later in the question. Calculate the total extension in the spring, and it tells you that the spring constant, so this value here is K, is 400. Okay, just going to check my units. This is in joules, newtons, and newtons per meter, all things that are fairly standard, so it doesn't look like I'm going to have to convert any units in this question. However, there are 2 steps to this answer. The first thing I need to do is work out what the extension is when in the spring, when that is the energy stored. So the first step is to find the extension. So if I rearrange this equation, I can put the numbers in first. So 4.5 times 10 to the minus 2 is the amount of energy, is equal to 1/2 multiplied by 400, that's the spring constant, times by the extension squared. So if I rearrange that equation, that is 4.5 times 10 to the minus 2 times by 2 divided by 400 is going to be equal to E squared. Well, if I want to find out E, I need to square root both sides. So if I square root all of that, I get just E. And so calculating what E comes out to be, that works out that E is equal to 0.015. Okay, so that's the initial extension of the spring. But then she says, then the question says that the student adds another weight of an extra 2 newtons. Okay, so now I need to use Hooke's law to work out the second extension. This is the first extension when you added, when she hangs the initial weight on the Newton meter. Now she's going to add another weight. So we know that force is equal to spring constant times extension. I don't need to use the energy for this one, so I'm not given the additional energy, I'm only given the additional force. So if I have a look, an additional force of 2 newtons, if the spring constant was 400, would give me an extension of 2 divided by 400, which would be 0.005 meters. That's also in meters as well. And so my total extension is just going to be those 2 numbers added up together. 0.015 plus 0.005 comes out to be 0.020. So 0.020 meters. Okay. Now there is another method where I can work out what the initial weight was, work out what the extra weight was. So for those of you who want to see that other method, it will get me exactly the same answer. Once I have worked out what the initial extension is, I can work out what the force was. So force is equal to the spring constant times by the extension. So if 400 times by the extension 0.015 will tell me that the initial force on the spring, so this initial first weight that she put on, was 6 newtons. She then added another 2 newtons, so the total force is now 6 newtons plus the 2 newtons it says that she adds a second, so the total force is 8 newtons. I can then plug that into the last part of the equation, and so if I rearrange the equation, an extension is equal to force over spring constant. I end up with 8 over 400, which is also equal to 0.02 meters. Okay, so I get exactly the same answer, it's just a different method for the same question. Okay, right, moving on to question 5. Now, question 5 is quite a tough one. If you're not sure on this, certainly 5.3 is. We'll tackle the first two first. And so, describe the a car aerial receives radio waves from a radio transmitter. Radio waves are transverse, and it tells you that sound waves are longitudinal. Okay, these are stock definitions that you just need to know, but I'll write them down and then explain them. So in longitudinal waves, these are where the oscillations are parallel to the direction of the energy transfer, but in transverse waves, the waves are perpendicular. And one of the ways that you can remember is that in the word, if I highlight it for you, in the word transverse, the T has got a nice little perpendicular shape. Okay, so the top of the T is perpendicular to the vertical, and so that will help you remember that the transverse waves are the perpendicular ones. Okay, and if you want a quick little diagram to help you remember as well, when you think about longitudinal waves, this is where you've got areas where there is spreading out and areas where they clump together, and so you've got areas of compression and areas of rarefaction here. All right, but each of these little parts of the wave will move backwards and forwards, and so they will move backwards and forwards, and the energy will move forwards, and so those directions are parallel to each other. Okay, each of these lines will move back and forth, and the wave will transfer the energy forwards. Whereas in a transverse wave, you've got like a rope, and the rope itself will move up and down. Okay, so the medium will move up and down, but the wave itself moves forward. Okay, and so those two directions, the up and down of the rope and the forwards direction of the energy being transferred by the wave, are perpendicular to each other. So that is a transverse wave. Okay, so that answers that 5.1. 5.2. You're given the radio waves have a frequency of 4.8 times 10 to the 9 hertz, and the wave speed of electromagnetic waves is 3 times 10 to the 8 meters per second. If ever you get a question that asks you to work out the speed of light, given some information, you should recognize that number as the speed of light. So if you have to work it out, you know whether you've done it right or not. It's asking you to calculate the wavelength of the radio waves. Give your answer to 2 significant figures. This is a 3-mark question. 1 mark will be, if they have put this in the answer, give your answer to a certain number of significant figures, then they expect you to write it to 2 significant figures. If you don't, you will lose a mark on this question. Okay, now let's just swap back to the red pen. So the equation you're after here is that speed is equal to, or the wave speed is equal to frequency times wavelength. If you want an equation triangle for this equation, V, F and lambda, so speed, frequency and wavelength. So if you want to work out the wavelength, then it is So you know how to use these equation triangles. If you cover up wavelength, then what's left over is v over f. So in this case it is speed 3 times 10 to the 8 divided by the frequency, which is 4.8 times 10 to the 9, and so your wavelength ends up being, on your calculator, 0.063. Remember, I think it is a longer number on a calculator, but two significant figures is just 6 and 3. Okay, so you've rounded whatever came after the second significant figure. You've rounded it up or down to 0.063. Or on a calculator, it might have presented as 6.3 times 10 to the minus 2. Both of those answers are perfectly valid. So, moving on to question 5.3. Describe how the radio waves reaching the car aerial produce signals in the electrical circuit of the car radio. Radio waves. This causes the electrons in the aerial to vibrate, okay, because you know that an electromagnetic wave is made up of an electric field and a perpendicular magnetic field, and so when that wave moves, it's not drawn very well, but when that wave moves through a vacuum or through the air, when it comes into contact with your TV aerial, okay, what it's the oscillating magnetic field causes the electrons in the aerial to vibrate back and forth. Okay, so you should remember from the unit on electromagnetism that if you've got a wire and you move it inside, so if you've got a magnetic field, if you move that wire up and down through that, and you cut the field lines through that magnetic field, the electrons in that wire will be forced to move one way or another, and creating if you move it in the same direction, it will move in one direction, you create a direct current. But if you move it back and forth, the electrons will be made to move back and then forth, and that is the definition of an alternating current, where the electrons are moving back and forward, side to side. Okay, so it creates it causes the magnetic field that's oscillating around the aerial, causes the electrons to vibrate, which generates an alternating current in the aerial. And to finish off answering the question, the electrical signal generated has the same frequency as a radio wave. So that is how a radio wave produces an electrical signal in a car aerial. Just to put that in a box, all of that is not required for the answer, but it might help you understand it a little better. If you need to revise this topic further, that's just going back to your revision books and giving this another look. We may go over this again in class. So that's question 5.3. Let's have a look at question 6, which is all about cars travelling stopping distance and braking distance. So in this question, a driver is tired. His reaction time increases from 0.5 seconds to 0.82. Determine the extra, not the total, but the extra distance the car would travel before the driver starts braking. So if the driver hasn't started braking yet, his velocity will remain constant at 15 meters per second. Anytime you have got constant velocity and it's not accelerating or decelerating, you can use the equation distance is equal to speed times time, because the speed is constant, or you may have it in your revision books as displacement, that's S, is equal to velocity times time. Okay, both of those equations are the same, except to just don't get caught out in this equation. When it's distance, the S stands for speed, and in this equation where you've got velocity, the S stands for displacement, a fancy word for, or the vector form of distance. Both the same equations. So anyway, distance is equal to the speed, which is 15, multiplied by the time, but it's going to be the increase in the time. So if the time was 0.82 and it changed to it was 0.5 and it changed to 0.82, the difference is 0.32. Okay, so the distance is equal to 15 meters per second times by 0.32, which gives you a final distance, an extra distance of 4.8 meters. Okay, equally you could do it using a graph. So if you get your ruler out and use your ruler to draw lines from the 0.5, so from the 0.5 you're going to draw your line. Let's get my line tool. So the difficulty with the first one is fairly straightforward. If you've got 0.5, it's clearly hitting the y-axis at between 5 and 10, which is obviously 7.5. So when the reaction time is 0.5, he travels 7.5 meters. But when his reaction time is 8.2, you have to be a bit more careful with the scales. So each of the small boxes is worth 0.2, so 0.8, 0.82, 84, 86, 88, 9. Okay, so you're going up the 0.82 line, but when you get to the graph and you go across, you have to be very careful not to make the silly mistake, because the scale is different on the y-axis. So there's 10, every 2 boxes is 1, so that's 11, 12, 13, 14 and 15. And when you actually look at where the black line crosses, it's quite hard to do on the screen here, but it is not exactly on 12. So if you have a look, this line is just a little bit above the 12, so it's somewhere between 12.2. It's not as far as 12.5, but it's not as low as 12.1. So actually the mark scheme gives you an allowance of anything as low as 12.2. So we're going to use 12.3 meters, and so the difference is 12.3 minus 7.5, which again comes out to be 4.8 meters. Okay, so there are 2 methods for that question. So moving on to 6.2. When the brakes are used, the temperature of the brakes increases. Explain why that happens. Use your ideas about energy in your explanation. This is your question, which is all about conservation of energy and energy transfers. So if you know that the kinetic energy of the car is going to decrease as it slows down, you need to talk about what happens to that energy. So the kinetic energy of the car decreases as work is done by the brakes. That's what's slowing down the car. This causes the thermal energy in the brakes to increase due to friction. So again, I'm using concise, short ideas to express, to explain my answers. So this is an explain question. You need to say why something's happening, not just explain what is happening. And again, I've used bullet points to get it's a 2-mark question, so I need 2 parts to my answer. And so using bullet points has allowed me to put my answers in a logical order and again tell that story of what's happening. So the kinetic energy of the car decreases as work is done by the brakes. What does that mean? That means that the thermal energy in the brakes is increased due to the friction between the brakes and the wheels as they move. Okay, so we're just going to move on to the next page. So in this question, a lorry travels 84 meters with a constant acceleration. This is that word acceleration in the question immediately tells you that you cannot use the distance equals speed times time equation. That equation is only for when there is no acceleration. Here it's saying that the lorry is accelerating. We're at 2 meters per second squared to reach a velocity of 9 meters per second. Calculate the initial velocity. The fact that it's used the word initial suggests that you need to be using the equation from the equation sheet, that the final velocity squared minus the initial velocity squared is equal to 2 times the acceleration times the displacement. So if we plug the numbers in that we're given the final velocity of 19, so 19 squared is equal to u squared, which we're trying to find out, is equal to 2 times the acceleration, which we are told is 2.0, times by the displacement, which is how far he's travelled, so 84. Okay, rearranging that equation, we can see that u squared is equal to 19 squared minus everything on this right hand side carried over, so 2 times 84. Okay, and so if we want to find u, we just square root both sides of the equation, so square root all of that, and we will find our answer to the equation for u. So that ends up being that u is equal to 5. If rearranging equations is something that you need to practice, I would use your revision books, and there will be examples of those questions. You need to go over how to rearrange that equation. Okay, so moving on then to question 6.4. Figure 9 shows how the thinking distance and braking distance and stopping distance for a car vary with the speed of the car. Now on the next page you are going to be asked to describe the relationship shown in figure 9. You should include factors that would affect the gradient of the lines. So I'm just going to talk about these lines quickly before I move on to the next page. So this one here, okay, is a straight line and is the thinking distance, and it is quite clear that that is a straight line with an increasing gradient, suggesting that speed and distance are directly proportional for thinking distance, so we're going to mention that in our answer. Whereas this line here, the braking distance, that line is not straight, that is a curved line. So we cannot say that speed and distance are directly proportional, but we can say that as speed increases, the distance will increase. Okay, but it is worth mentioning that it is not a directly proportional relationship. And finally, the same applies for stopping distance. Okay, but you can see we should know that the stopping distance, that's the yellow line, is equal to the braking distance, which is the green line, plus the thinking distance, which is the blue line. So at each of these occasions, if you want to get to the yellow line, you just take the blue line and the green line, add them together, and you get the point on the yellow line there, because stopping distance is equal to braking distance plus thinking distance. Okay, that's going to become important in our answer as well. So moving on to the next page then to answer the question. Describe the relationship. You need to mention all 3 lines. Describe the relationship shown in figure 9. So first we're going to talk about thinking distance and the factors that affect thinking distance. If you're on drugs, on alcohol, if you're tired, if there are distractions, then you would expect your thinking distance to increase. And if the thinking distance increased because you were tired or on alcohol, etc., you would expect the gradient of that line to be steeper. Okay, so the faster you're going, the more the thinking distance is going to be affected. And it shows, we're going to mention that the graph shows that the thinking distance is directly proportional to the speed. Okay, so I'm going to use subheadings in my answer. And I've made my 2 points. So there are 3 things I need to talk about: thinking distance, braking distance and stopping distance. So I'm going to try and make 2 points about each one to make sure that I get my 6 marks. So I've mentioned the factors that would affect thinking distance: 1, 2, 3, 4 things that would affect the thinking distance. I wouldn't need to get all of these to get the marks, but I should get most of them. I do need to make sure, because it asks how it would affect the gradient of the lines. So I would say that it would increase the gradient of the line of the graph if I was on more drugs, more alcohol, or if I was more tired, or there were more distractions. I've also mentioned that the graph shows that thinking distance is directly proportional to speed. Okay, let's move on to braking distance. I can't say that thinking distance is directly proportional, but I can say that as braking distance increases, the speed increases at a greater and greater rate. That's shown by the fact that it is a curve upwards. So if you look at the gradient initially, so for braking distance it's got a very shallow gradient. So initially the braking distance increases at a low rate as speed increases, but later on, as speed continues to increase, the rate at which braking distance increases is getting larger, faster, because it's shown by the fact that there is a steeper gradient later on. Any curve that curves up is showing a shallow gradient at the beginning and a greater gradient at the end. So the way that I put that in an answer is to say that the braking distance increases at a greater rate as speed increases. So that's not saying it's directly proportional, you're talking about the rate of change increasing. Okay, I also need to mention the factors that are affecting braking distance. So poor brakes or poor tyres or icy or wet roads, you can't just say brakes or roads, you need to say what about them will increase the braking distance. So an increased mass, a poor brakes, poor tyres, icy roads, wet roads, all increase the braking distance. And finally, anything that increases the thinking distance or the braking distance is going to increase the stopping distance. And the reason why we know that is because stopping distance is equal to the thinking distance plus the braking distance. So it's worth saying that anything that increases thinking distance or braking distance will have an effect of increasing stopping distance. And because the shape of the graph for braking distance is not linear, then stopping distance won't be linear either. And so it is also worth tacking on that last sentence that stopping distance also increases at a greater rate as speed increases, and that would easily get you 6 marks. There's quite a lot there. It's quite hard to write, quite small on the screen, but I'm sure if I was writing on a page, I'd be able to fit that into that space. So moving on to the very last question then, question 7. Describe so figure 10 shows the horizontal forces acting on a man swimming in the sea. Describe the movement of the man when the resultant force is 0. This is a 1 mark straight out of the book answer. Okay, when the resultant force is 0, you have a constant velocity. Okay, this is Newton's first law that says that if there is no forces acting on an object, i.e. 0 resultant force, then an object will continue at a constant velocity, or it will stay stationary. But as the swimmer is clearly not stationary, because he is swimming in the sea, he will continue at a constant velocity. Okay. The man increases the force A. Explain what happens to force B and to the movement of the man. So you have to explain what happens to force B and to his movement. Okay, so first of all, if man increases force A, we know that force is equal to mass times acceleration. If there is, if you've now got a force, an increase in force A, there is now going to be a resultant force to the left because A is going to be bigger than B. Okay, so that's clearly the first thing to say, that the man will accelerate. Okay, as he does that, because it's just like the free faller reaching terminal velocity, as a skydiver gets faster, air resistance will increase, and so it is the same with the swimmer. As the swimmer starts to accelerate, then the drag in the water, force B, will start to increase, and it will continue to increase until those two forces, A and B, are balanced again. And when those two forces are balanced, you will be back in the situation where you have got equal forces. So force B now matches a larger force A, but the resultant force is 0 newtons because these two forces are now the same again, because drag has increased due to its increased speed. And when there is a 0 resultant force, you have a constant velocity again. So that is finally what will happen to the man. He will continue to move at a new constant velocity, but that constant velocity is faster than it was before, because he was obviously accelerating due to an increase in force A. Okay, moving on then to 7.3. This is all to do with vector diagrams, which we did all the way back in year 10. So you might want to go back over vectors. So there is a boat is moving through the water. There is a 3,000 Newton force west, a 1,000 Newton force south. Determine the magnitude and direction of the resultant force. So resultant forces, you can, when they are acting in parallel directions, you can simply add them up and find the difference. So if there's 10 newtons to the left, 5 newtons to the right, the resultant force on that block would just be 5 newtons to the right, because you did 10 minus 5. Okay. When you take result forces and they are perpendicular to each other, you can add them together. So if you were to find the resultant force of a force acting up and a force acting right, the resultant force would be acting in that direction between the two. And you can use a scaled diagram to work that out. So if I put my boat over here in the corner, and I want to try and use the full scale of the grid available, it would be very easy just to work out 3,000 newtons west by doing 1,000, 2,000, 3,000, and working out the force south, doing same scale. It's important that the scales on both the x and the y are in the same because you're going to use your resultant ruler to measure the resultant force. It's but you can see I would be able to use the whole grid. So I'm just going to undo that. Okay, and I can use 1,000, 2,000, 3,000 newtons for my force west on my boat, which is this blob here, so 3,000 newtons, and using the same scale, 1,000 newtons south. And so my resultant force is an arrow from the point all the way over here. Now obviously you're going to use a ruler. It's quite hard for me to use one on the screen, but if I did get a ruler and I could measure the length of that line and compare it to my scale. So if I try and do that quickly. So my ruler is not to scale the same scale as yours, but if I move the ruler up to that line and I measure the length of that line, compare it to the length of my 3,000 Newton line, I can see that that line is clearly longer. And if I use a simple ratio, I can see that my 3,000 Newton line my 3000 Newton line is on this scale 12 centimetres, but if I try and measure, if I try and measure the length of my diagonal line, that is going to be somewhere, it's quite hard to see with the red line, about 12.6 centimetres. So I want to know, I'm trying to work out what the resultant force is, but I know that line is about 12.6 centimetres. When you do this on paper, it would be easier to work it out, but what I'm going to do is 12.6 times by 3000 divided by 12 would give me an answer of 3,100 newtons to two significant figures. So that's the direction of the resultant force, and I can either, if I wanted to, use a protractor, and I can work out that this angle here using a protractor is about 18 degrees. So that angle there is 18 degrees. So I can either say that it is 18 degrees from the horizontal on the horizontal line, or if you know how to do bearings, if I take north as 0, then that angle there, okay, is going to be 270, so that's 3/4 of the way around the circle, minus that 18 degrees. So, or it has a bearing of about 252 degrees from north. Okay, so you should have done those in maths, taking bearings. That's so your answer 3000 is 3,100 newtons, and it is 18 degrees from the horizontal, or 252 degrees from the north. So the next question: the force to the south of the boat increases. What effect does this have on the resultant force of the boat? So you need to talk about the resultant, the magnitude and the direction. Okay, so if that is a scale diagram of what you had before, the resultant force being those two forces added together, if I increase the size of the force to the south, then my resultant force not only becomes longer, but it also is directed more to the south. Okay, so we can say that the magnitude, in other words, the size of the force, increases, and we can also say that the direction of the force moves more towards the south. This question, I know it looks quite messy, there is a lot of working out there, but again, if I just highlight the bits that you wouldn't necessarily require, so you don't need to show that working out necessarily, or this bit here. The angle you could just measure once, doesn't have to be that untidy. All of this isn't needed. If you go back and revise resultant forces and vectors in your revision books, then you'll see that this doesn't have to be a complicated topic. We may revise this more in class. So, didn't mean to do that. So moving on to the very last question then. Oh no, that is it. That 7.4 is the last question. So that's the whole of paper 2. There's quite a lot to that. I hope that's been useful. And if it is, let me know, and I may find time to do another paper for you as well.